All right, we are going to do the semester at a glance video so that you can help remember things from the semester for review for your midterm. Here we go. I'm going to try to do this in 30 minutes. Clock has started. First unit, we talked about a lot of terms. It's the introduction to statistics. And what is statistics? It's kind of like the science of analyzing data. I'm actually going to type that. Okay, so collecting, analyzing. There's the statistical process where we ask a question, We will then collect data. We will analyze the data, and then we'll make a conclusion. Okay, that's kind of the statistical process. And we first figure out the variables and kind of the individuals before we talk about the variables. Individuals is who we're studying. Or what we are studying. Okay, variables is what data we are getting from the individuals. So if we're saying ducks, we could get the variable to ducks wingspan. There's two types of variables. There is quantitative and there's qualitative. Wingspan would be quantitative because you get a number. Qualitative would be overall mood of the duck. Okay? The sample is the amount of something that you are taking. Okay, so let's say we got a total of 20 ducks from a lake. Okay, the sampling frame would be, hey, I wanted to get, I got my ducks from the lake, so the sampling frame would be all the ducks around the lake that I could get. But the population would be all North American ducks. So it's really important that we go from a population, which is like everybody that we're trying to kind of, figure out more of, to, well, I can't talk and grab everybody from this population. So instead of looking at everybody, I'm going to just look at some people. The some people that I get, or the some things that I get, are my sample, but that sample comes from a sampling frame. So in this case, with the population, we said maybe we're looking at the wingspan of all North American ducks. Well, I can't get all North American ducks, but I live near a lake, so I'm going to look at ducks around my lake, and my sample is 20 ducks. Okay? The census would be if we examine or get data from every single individual of the population. Okay, so that would be if I was able to, grab every single duck and get their wingspans. Now we don't really do that, so the kind of art of statistics is that instead of looking at censuses, we are going to produce samples. And now samples will produce statistics. Didn't throw that on in there. I'll do that up here. Okay? So a sample produces a statistic. It is typically the mean of a sample, or it is information from your gathered data in your sample. If you were able to talk to every single person and make a census, you would produce a parameter. Remember, a parameter is a mean for a population. but kind of the art of statistics is that it is very tough to do a census. So instead of doing a census, we will take a sample. That sample will produce a statistic, and that statistic we will hopefully say will tell us what the parameter actually is. Okay? So instead of a census, we take a sample to produce a statistics. Hopefully the statistic will be the same or close to the same as the parameter. Okay? Now we're hoping that our statistic is reliable and the data is reliable. Reliable data means data is close to being accurate, perfect every time when collected. It is the inverse of variability. So reliability, good reliability would mean low variability. So that means if I'm taking, you know, a measurement of something, I want it to be consistent and perfect every single time. Okay? Now, if we take our data and all of a sudden we have a bias compared to what it should show, bias means that the data is off in a certain direction from what it should show for whatever reason. Typically what we talk about is, hey, I want to look at the wingspan from my ducks. Well, let's say that I know that the parameter for my ducks is ducks in North America should have an average wingspan of 12 inches. But let's say my sample produces a statistic that is 10 inches. And maybe after I did all of my samples, I saw that like one duck is 10 inches, one duck was 9 inches, one duck was 10 inches, one duck was 10 inches, one duck was 9 inches, one duck was 10 inches. All of my data is really close to 10, so I would say that this data is very reliable. However, all of my data is lower than the actual parameter, so we would say this is biased because it's lower. Now, why would my data of my ducks be lower than what it should be? Well, because I took a sample. I took a sample from my lake when, you know, maybe the lake is not a good representative sample of all North American ducks. Okay? There are two types of studies where we will produce data. There's an observational study where we're just collecting data. And there's an experiment where we collect data after imposing a treatment. Now, we collect data, but we have no influence over the data collection. So we do not affect anything. We are just strictly observing. But the experiment imposes a treatment, which will hopefully show a comparison and then gives us a conclusion. Confounding variables, we typically talk about a confounding variable as being something that is lurking in the background that is causing a change, but is not particularly being studied. We talked about with ice cream sales and drownings. Ice cream sales are going up, drownings go up. Does not mean that ice cream sales are causing drownings. Probably the confounding would be the temperature. Okay, so that was unit 1. Unit 2, we then looked more into experiments. Experiments is how we are going to set up a situation where we can collect data and have some comparison. Okay, and the experiment imposes treatments. Treatment is whatever you are doing to the group to produce an outcome. computer is slow. Okay, whatever is imposed on individuals to produce an outcome. The explanatory variable is typically the treatment. It is what is being done. The response variable is the outcome that you're measuring. Typically we talk about experiments like with drugs. So maybe we're talking about this drug HP5. We're going to take the drug and we're going to see if it is improving our cholesterol. Let's not do cholesterol. Let's do, let's do cholesterol. I can't spell cholesterol. All right. So explanatory variable would be the HP5, or what is being done, what is being taken. We are asking our patients to take HP5. Response variable would be our cholesterol levels. If they go down with HP5. Now we could do this experiment multiple ways. We could do a completely randomized design. This is CRD. Okay. In a completely randomized design, you will take your subjects. Let's say you got 50 subjects. You will randomly select them and put half of them to receive the drug, and half of them will get something else or nothing. We typically like to give them a placebo. This is a control group, and then we will look at the results. We'll compare the outcomes, okay? We could do a block where we will separate them through some distinguishing factor. Maybe we want to look at HP5 for men versus women. So we'll separate our individuals by a characteristic, then impose our treatments using our CRD. So let's say I think men are going to respond differently from HP5 than women. Well, let's say out of the 50 people, 30 of them are men, 20 of them would be women. I would then go 15 would receive the drug out of the men, 15 would receive a placebo, and then out of the women, I would do 10 would receive the drug and 10 would receive the placebo. And then I'd compare my results, okay? We also have matched pair. Matched pair, there's two different types of matched pair. First different type of matched pair is everybody gets both treatments. Everyone gets both treatments. So that means for 1 week, we would get the drug. The other week, we wouldn't get the drug, and we'd compare how we did on the drug versus how we did off the drug. We'd randomly assign who gets the drug first and who didn't get the drug first. That way it's not everybody getting the drug first and everybody not getting the drug second. Second one is we match our individuals by, body type or just some certain characteristics we want to match up our individuals. By characteristics. One's going to get the treatment, the other the placebo. Okay, so those are matched pairs. Either you can take 50 people, we'll take 25 who are going to get HP5 first, and then they're going to get the placebo second. And then the other 25, they're going to get the placebo first, and then the HP5 second, and compare the results. Or you have 50 people, 25 and 25, they're matched up by, starting cholesterol levels, and then half of the ones that have the same starting cholesterol levels as these half get HP5, the other one get the placebo. We look at the results. Okay, key to good experiments is having a control group. So a baseline. This control group will receive the placebo. The placebo is, instead of an actual drug, it will be like a fake drug. so that we can eliminate possibilities of people, knowing or not knowing that they're receiving the drug. We say, hey, you may or may not be getting the drug, so you won't have kind of, a preconceived, oh, I am taking the drug, that means I'm definitely getting better. So, we have something called the placebo effect, where we think that we're taking a drug and we feel better. So they do not think that they not know if they are really on the drug or not. Okay, that will help with our results being more, tied to the drug rather than psychological. There are single-blind or double-blind studies. We'll talk about single-blind. That is when the patient does not know if they're getting the placebo or actual drug or whatever else, whatever treatment. Okay, that is typical what you need to do in an experiment. You want it to be single-blind. Double-blind is when both the patient and the doctor who is assessing, does not know what's getting what. Only the researcher knows. The researcher has the key. We want all of our experiments to be confidential. That means names are not released. But they also could be anonymous and have anonymity where names are not known to the researcher or the public ever. Okay, so that means neither confidentiality. We could have a situation where like the researcher knows the names of all the subjects, but anonymous means there's no names involved at all. Okay, so that was experiments. That was Unit 2. We then went to Unit 3 where we displayed data. Now we talk about bar graphs. Bar graphs good for qualitative data. So out of my 50 ducks, who was feeling sad, okay, and happy? We can say, oh, 10 ducks felt sad, 20 ducks felt okay, and 20 ducks felt happy. Okay, that's perfect bar graph. Now, instead of a bar graph, we could have also done a pie chart where I said, oh, also good for quantitative data. Perfect thing for a pie chart is that you got to make sure that they add up to 100%. Let's see, 40% said that they were happy, 40% said that they were okay, and 20% said that they were sad. Okay, so not to scale, but you get my drift. Okay, how do you find the percentages? Remember, a percent is a part out of a whole. Okay, part out of a whole is a percent. A line chart is good for quantitative data over time. Okay, so we would have like years, and then we would have our data. So maybe car sales, or like Volkswagen car sales or something after the diesel things. So car sales have gone down over time. We would use a line chart for that. Okay. Now there's a couple of things that we want to get from our data. We have measures of center. Mean is the average. So add up all the data and divide it by the total number. Median is the middle number. We have measures of spread, which is a range or an interquartile range. The range is just our max minus the min. The interquartile range would be our third quartile minus our first quartile. Okay, this is used for box plots, which we'll talk about in a second. Standard deviation is a value that we can calculate, which can be calculated and shows kind of the average distance data is from the mean. Okay. let's show you how you can calculate all those things. Let's say you have data. Remember, we have our calculator. We can always go to stat, edit, and we can enter in data into L1 or L2. Let's say I have some data in L1, and I want to calculate all those things that I'm talking about. Well, stat calc, one var stats, if we press enter, we make sure, let's say I want L1's list. You press calculate, and it does everything. X bar is the mean. This is like the sum of all the values. You don't use that ever. Here is the sample standard deviation. Here's the population standard deviation. They're two different numbers. It all depends on, like, if we have a sample, we want to kind of spread things out to account for more things if we have outliers that are not taken care of. If I had a population, this is the population standard deviation. Sometimes we'll use one versus the other, depending on what type of data we are given, whether it's a sample or a population. N is the total amount of data points that I have. We should be familiar with that. Now, if we keep going down, we see we have the minimum value. We have the median, that's the middle number. We have the first quartile, which is the middle of the first half of the data. We have the third quartile. We have the max. And that's it. That's all of our data. We can do max minus the min. We can do Q3 minus Q1 to find the range and the interquartile range. Okay? Now, ways we can display data, besides pie charts, line charts, graph charts, or box plots. Box plots typically look like this. And what's important about box plots is that our data is spread out into quartiles. 25% of our data is between the minimum and Q1. 25% is between Q1 and our median. 25% between our median and Q3. And 25% between Q3 and our max. If you want to create a box plot, you can just go second stat plot. Turn your plots on. We'll go down into our box plots, into our type. And again, you can do a lot of other ones here, but let's go into our box plots. Our box plot is either this guy or that guy. This first box plot is the one you want to use because it also does a great job of calculating your outliers. We press enter, we graph, and we make sure we go zoom 9 and graph. If we press trace, you can see our minimum value, our Q1, our median, our Q3, and our max. Looks like most of our values are between Q1 and the median Q3. Okay, so the interquartile range is kind of large, but it's close to our overall range. If we had an outlier, if for some reason I came in and threw in a value like 1400, what we will see if we graphed our box plot, and I zoom 9'd it, is a dot. Well, what is that dot showing? That dot is an outlier. An outlier is an unusual feature, and boom, we can see when we graph our box plot, that unusual feature coming up. Okay, so that's a box plot. We also have a stem plot. A stem plot is when we list off, typically the first two values or the first value. Let's say I have home runs per season by some baseball player. So I'd say, okay, 1, 2, 3, 4. Maybe in this first season he had 11 home runs, and then the second season he had 14. Third season he had 33 home runs. Fourth season he had 45. Well, this would be the stem plot showing that data. Okay. Now he didn't have any 20s, but we don't skip the 2. We make sure we include the 2. We can also do a back-to-back stem plot. Back-to-back stem plot is when I will have data both to the left and to the right. So maybe I want to compare this 4-year baseball player to another baseball player who got 20 home runs and 21. Notice I go from inside outside. And then he got 31 home runs, and then he got, let's say after the 31, he got 10. Okay, you can kind of compare the two, saying, okay, maybe this overall's mean is maybe better than this guy. Maybe this guy had the higher overall, high end, so maybe he's better. Anyways, you can do comparisons that way. Histogram is a frequency chart. It looks like a bar chart, but it's not. So what happens with a histogram is that we have bins on the bottom. So like from 0 to 10, from 10 to 20, from 20 to 30. And then we see how many set pieces of data is from 0 to 10. We could do a bar chart, frequency chart for both of these home run hitters. So we have 10, 11, and 14. That is 3 between 10 and 20. That's starting at 10 going to 20. So I'll have 3. Then we have 20 and 21. We had 2 between 20 and 30. So that there. Then 31, 33, we'd have 3 between 30 and 40. 2 between 30 and 40. And then 1 between 40 and 50. Okay, and that is your histogram. Now, how do we graph a histogram? We can do it in our calculators, either by hand, or let's say we want a histogram of here. We would go into stat plots, make sure our plots are on, and we would select this third graph, which is not a bar chart, it's our histogram. Again, zoom 9, and you see the same type of graph that we just saw. And if you go trace, you can see here are the bins from 650 to 690. There's 2 of them. And then between 690 and 730, there's 1, there's 1, there's 1. Okay? So that is a histogram. Now, from looking at histograms or stem plots and from box plots, you can talk about the skewness. The skewness is if the mean is getting pulled in a direction. Compared to the median. So many students struggle with this. Graph of data like this, the median would actually be lower than the mean. The median would be down here, the mean would be up here. We would say this is skewed right. If you had data that on a histogram was displayed like this, the median would be here, but the mean would get pulled to the left. The mean would be lower than the median. The mean is getting pulled towards what we consider outliers. So this would be a left skew. Then we would have data that ends up looking like a bell curve. The median and the mean would be the same, and this would be no skewed or symmetric. Okay, there's other types of data that we can see. We can see uniform. This is uniform. We can see modals. This is bimodal, where we're focused around 2 different areas. Okay. And if you were asked to describe data, we typically want you to describe it using this mnemonic CUS, where you talk about the center, any unusual features, which is like outliers, the spread of the data, which is either the range or the standard deviation, and the shape. Is it skewed? Is it symmetric, etc.? Okay, and that was Unit 2. And don't forget that the measure of center is either the mean or the median. Typically, we like to use the median if we're talking about data that is skewed. We'll talk about the mean if we have data that's symmetric or other. All right, well, then we got into specifically normal distributions. Okay, that's symmetric distributions. Okay, and symmetric distributions like this. Now, this is like a histogram. Okay, so if you did a histogram, the bins would fall like in here. Okay. but we kind of use this curve to show the density of all of our data. Okay. Now it's important to know that 100% of our data is underneath this curve. Now it's best with normal distributions to talk about a specific example. So let's say last test results were normally distributed with a mean of 80 and a standard deviation of 5. Great thing about normal distributions is that the mean and the median are the same, and we do the spread of data by the standard deviation. Standard deviation is super important when it comes to normal distributions. And plus 1 standard deviation, we would just add 5 to my score to get 85. And then I add 1, I'd get 90, add another one, we go to 95. Usually 3 standard deviations is enough. You go any more, and you will be talking about very, very rare occurrences. Okay, so this is our scores, but it's also important that we know that we can list normal distributions as in terms of distances away from the mean. And this is where we have a z-score. A z is a distance in terms of standard deviations from the mean. Okay, so 80 is a standard deviation distance of 0. So I'll put z's in red. We'd say this is 0. This would be 1 standard deviation away from the mean. 2, this is 3. This would be -1. A negative z-score would mean you're below the mean. This would be -2, -3. Okay, and what is really great about normal distributions is what we can do, which is do a lot of calculations for, the probability of the percentage of our data that is between any 2 values. Okay? And it starts with the empirical rule. The empirical rule is 68, 95, 99.7, which means 68% of our data is within 1 standard deviation of the mean. 95% of our data will be between 2 standard deviations away from the mean. And 99.7% of our data is between 3 standard deviations away from the mean. That means 99.7% of students on the last test would get between a 65 and a 95. That means 68% of students got between a 75 and an 85. That means 95% of students got between a 70 and a 90. Okay, and this is just a hypothetical situation, but that's the empirical rule. Okay, 68% is here. That means 34% is in one of these boxes. It's also important to know that since this is 100% and the mean is halfway in between, that 50% is below the mean and 50% is above the mean. Okay, very important to understand that. Okay, now let's do some calculations. The z-score is a standard deviation distance from the mean. You can calculate it using this formula. You just subtract the distance in terms of the units. So that would be your observation minus your mean. And then you turn it into standard deviations by dividing it by the standard deviation of your data. Okay? So let's say I have a score of 86. I'll say z of 86. What is that? Well, 86 is my observation. My mean was 80. My mean is 80. My standard deviation is 5. So 86 minus 80 over 5 becomes 6/5, which is 1.2. So if I had a score of 86, that would be 1.2 standard deviations away from the mean. Okay? Now we can do some things using some functions in our calculator, like finding the percent given an observation. So what is the percentile, percent below, or percent above? Now it's very important that we know that usually we go down to -3 and 3, but we like to just kind of top things off at 10 standard deviations from the mean, greater than the mean, and -10, less than the mean. And here's the question: what percentile was somebody who got a 92? Now it's important to know that percentile is what percent of my class got below a 92. Okay, percent below a 92. So let's go up to our graph. If I got a 92, the question is, what is the percent below. So what is this area here? Okay, I always like to have a graph to know what I'm looking for. I know that 92 is up here, and I know that my value that I'm going to get is going to be very, very large. Okay, it's definitely larger than 50. It's going to be probably, you know, in the 90s potentially. Okay, so percent below a 92 for my score. Well, first I'm going to take my z-score and find that. So I got 92 minus 80 over 5. So that's 12 divided by 5. That is going to be 2 and 2/5, so that's 2.4. And I can just do that in my calculator. Now, if you do it in your calculator, make sure you have your observation minus your mean in parentheses. Do that all at once and then divide it. Okay? So, now, to turn z's into percent, we will use the function normal CDF. Okay? Now, where's normal CDF? In my calculator, I'll go to second dister. And remember, normal CDF is down here at 2. Okay? Now, it says lower and upper. Well, this is when we're going to use the z's that we have. So if I have 2.4, I'm going to go normal CDF. And now I go back up and I say, between what two values? Well, I wanted this area here. So we're going from the 2.4 to the minimum value that we could have, which is negative 10. So I'm going from here, which I found was a z of 2.4, down to negative 10. So the lower is negative 10. The upper is 2.4. So in my calculator, I will type in the lower of negative 10 and the upper of 2.4. I then paste. And it gives me my percentage. Turns out 99% of students got below a 92. Crazy. Okay, and that is correct. Okay, so you use normal CDF to turn observations into percentages. Now we could go the opposite way, and we could find the observation given the percent. So for given percents, what do we have? What do we have? So the question is, what score do you have to get to be in the top 30% of all students? Now we will use inverse norm to change a percent into a z. Okay. Now the only important thing to know about inverse norm is it's always the percent below. So let's go up and talk about being in the top 30%. Let's remove this. Top 30% would be, you know, approximately this area here. Well, inverse norm can't take that value and turn it into the z we're looking for. Instead, you would use the fact that if 30% is up there, 70% would be below that. Inverse norm wants the percent below. So inverse norm wants the 0.7. So I'll do inverse norm of 0.7 to figure out the z value that I want. Second dister, inverse norm 0.7. And I get 0.5244. Now that is a z value, and I don't want to kind of delete that or move that around because round that. I want the entire decimal. Okay. Now I have that. What I'm going to do is turn that into an observation using my formula. Because I know this is a z, well this is a z. It's not a percent, okay? So I have observation minus my mean over my standard deviation. Let's fill out the information. I know the mean is 80. The standard deviation is 5. To solve for the observation, I'll multiply and then add. So I have that 0.544, ... I'm going to multiply by 5, and I'm going to add 80. And that's going to be my observation. in my calculator. This value will be multiplied by 5. I'm going to just save the value and not round it at all. Add 80, and turns out all I needed to get is an 82.62, and I'll be in the top 30%, or higher than an 82.62. Okay, so that's the score I could get, and I'm in the top 30% of all students. Okay, so again, normal distributions, symmetric curves, very cool because we can calculate so much stuff from them, because we have calculator functions that really tells us specifically what you have to be in the top 10% or in the top 30% or in the bottom 10%, the bottom quarter. Okay, all can be calculated using our knowledge of z-scores, using normal CDF, which turns z into a percent, and using inverse norm, which turns a percent into a z. Okay? And then finally, the most recent unit was on scatter plots. Scatter plot is a graph of two sets of data simultaneously. Okay? Typically, we will have a explanatory variable and a response. And based on a certain time or just in order, we will have data being plotted. Okay? Correlation shows the strength of the relationship. I'm going to go back to typing. Strength of the association of the explanatory data versus the response data. Okay? Correlation have values between -1 and 1, nothing outside of that. If you have a value of 1, you are linear. Strength of the linear association. You are 1, you are linear, and you are positive, which means as your x is going up, your y is going to go up. 0, which means there is no linear association. -1 would be extremely negative. It would be extremely linear, but it would be a linear negative association. That means as your x values are going up, your y values would go down. Okay? It is not in a unit. It's just the strength. Closer to 1, the stronger the linear association, whether it's positive or negative. Variance is your R squared. Now, variance tells you the percent association between the change in your x variable compared to the change in your y variable. This is just a statement that you need to know that R squared gives you a percent association between your x's and your y's. Your line of best fit is y equals some ax plus b, which is the line that best fits your scatterplot data. It helps show whether you have a positive or negative association by looking at the slope. So if I had my scatter plot that looked like this, probably my line of best fit would fit here. Oh, not like that. Fit right here. Okay? It's the line that will kind of decrease our residuals, which is the point to here, and that's something we can know as a residual. It is your observed value minus your predicted using your line of best fit. Okay? And the line of best fit is a line of best fit because it minimizes your residuals. Okay? Now it's important to understand you can interpret the slope and the y-intercept of your line of best fit. The slope, which is the A, remember slope is, y's over x's. I'll have to use my graph for that. So it's the rise over run. Well, it's the change in the y's over the change in x's. That means if x goes up 1 unit, and typically we'll have A is equal to, 5. Well, I write that as 5 over 1. As x is going up 1, y will go up 5. Now, if this was negative, I'd say as x is going up 1, y would go down 5. But it's very important to know that x and y is going to mean something. So explanatory, let's just say this is temperature, and this is the ducks at my lake. The ducks at my lake like higher temperatures. As the temperatures grow, there are more ducks at my lake. Okay? Ducks always go to nice places in the winter, right? So temperature goes up, more ducks in my lake. It's important to know that if this case my slope was 5, let's say it's positive 5, y would represent the ducks, x would represent my temperature, right? You have to understand what is x, what is y. So that means, yeah, as x goes up, well, as temperature goes up 1 degree, my ducks are going to increase by 5. So I'm going to have 5 more ducks, okay? The slope is the A. We also have to talk about the y-intercept. The y-intercept is the B. The B occurs when x is 0. So if we look at this situation, let's say my line of best fit for this ducks was y equals 5x plus 2. So the interpretation of my B, when x is 0, I'd have y equals 5 times 0 plus 2. I'd get y equals 2. Well, x is 0. X stands for temperature. If the temperature is 0, I'd have 2 ducks at the lake. Okay, it's important to know that you can use your line of best fit to predict. So that means I can say if the temperature is 40 degrees, how many ducks can we expect? Well, again, you have the equation y equals 5x plus 2, where x is temperature and y is ducks. You have to understand what is x and y. If temperature is 40, you'd plug in 40, and you'd see that you'd have 40 times 5 is 200, 202 ducks. Okay? Now, you could also go the other way. If I have like 400 ducks, how hot is it? Well, 400 ducks would be the y, and I can solve for x. I get 398 divided by 5, which is 79.6 degrees. Okay? So that's it. So we have our interpretation of our slope, the interpretation of our y-intercept. Okay? We can also find the equation given our stats. Actually, it turns out the line of best fit, y equals ax plus b, comes from certain things. The A, or the slope of the formula, comes from the correlation between our two data times the standard deviation of a y set of data divided by the standard deviation of our x set of data. And also the B, we can calculate just by, finding A, and then we can just take our y bar and our x bar and plug that in, and we'd find that B is y bar minus A times x bar. Okay, those are formulas that you will be given, you'll be able to use. So let's just say for test grades, for a math test, the mean was 80. The standard deviation was 5. And let's say for an English test, the mean was 75 and the standard deviation was 7. Find your equation of the line of best fit for your data. And typically we'll have the x's as our explanatory and our response. Hopefully we'll try to say that math is going to predict English scores. But who knows? It will depend on the question. We'll get A is equal to, and the correlation between the two is 0.7. And we need that as well. You'd say A is 0.7 times SY over SX. You do the calculation. You get 0.98, so that's the slope. And then you find the B, that would be the y bar, minus A, which you just found, times x bar. (75 minus 0.98 times 80. And you get negative 3.4. So I get y equals 0.98x minus 3.4. Okay? Then, if they ask you to say, if I got a math score of an 85, what would be my English score? Well, you'd plug in 85 for x, and you find y. They would say, hey, what does the slope mean? The slope means, as the slope is 0.98, you put that over 1. You'd say, as x is going up 1, y is going to go up 0.98. So that means as my math score increases 1 point, my English score is going to increase 0.98 points. And they might say, hey, what's the y-intercept mean? The y-intercept is when x is 0, you get negative 3.4, which means if I got a 0 on my math, I'd get a negative 3.4 on my English. Doesn't really make sense, which is why we talk about only using our line of best fit to predict values close to where our data is centered, not further away. Okay? That is statistics first half. Rewatch if you have questions. Thank you.